Yeah, thank you. Hi, everyone. My name is Sappey. I'm a fifth-year graduate student at UC San Diego, working with Quinn Konopacki as well as the KPIC team and high-spec team. And I'm going to be talking today about high-resolution infrared spectroscopy at Keck. And I forgot to put the caveat that we're also doing fiber-fed spectroscopy at Keck today. So an open question in the field of exoplanet sciences is the formation of gas giants, and two mutually inclusive theories about their formation in protoplanetary disks are core accretion and gravitational instability. And so in the core accretion scenario, dusty particles form or begin to stick together and form planetesimal bodies. And then if you're creating a gas giant planet, they then accrete gas to form that planet. On the other hand, gravitational instability forms planets by kind of gas and dust collapsing from an unstable protoplanetary disk. And in the core accretion scenario, these processes are taking place depending on the mass and metallicity of the disk from about 1 to 10 AU, whereas in gravitational instability, the processes are taking place on the scale of kind of, let's say, 100 AU or something like that. So what you really want is a way to be able to distinguish these populations. Unfortunately, we can model these processes, add the effects of migration, and what you end up seeing is these two populations are beginning to overlap, not only in the semi-major axis space, but also in the companion mass space. So just by looking at something, we can't really tell necessarily how it formed a priori. But maybe you can look for a molecular abundance, some signature, something to tell you where these brown dwarfs and exoplanets are forming in their protoplanetary disk. We have thought for a long time that the C to O ratio might tell you something about where planets have formed. Isotopologues is another really cool option. An isotopologue is the ratio of two isotopes of an element. So say 12 carbon over 13 carbon with one extra neutron, or potentially a volatile ratio. So for example, sulfur to oxygen ratio. And so in each of these cases, you have something changing with orbital separation and abundances over time that you would hope to measure. And so I think personally, one of the best ways to do this is through high resolution spectroscopy. Why? Well, we can resolve individual absorption features in these spectra. And from their position, intensity, and overall kind of morphology, we can begin to derive properties such as the radial velocity, the spin, maybe weather on the surface of a brown dwarf or exoplanet, and other atmospheric parameters and compositions. And so Dino explained really well how we do this with spin in his talk. And so Luke also gave an excellent talk on KPIC yesterday, but I'll just go over quickly how we're doing this with KPIC. So in KPIC, we place 4 single mode fibers in the plane of the telescope. We then use these single mode optical fibers to route light to the near spectrograph where they're dispersed at a resolution of 35,000. We then use a data reduction pipeline to extract spectra. And if you place one of these fibers over the location of your target object, you will have a combination of star and planet light in that fiber. And then we're able to use this high resolution spectra to do our science. So one target object that I want to tell you about that I've been working on is HC206893b, mouthful. It is a 26 plus or minus 4 Jupiter mass LT transition spectral type object. It's separated about 250 milliarc seconds from its host star. And it is the reddest known substellar companion. It has a J minus K magnitude of 3.36. So this is a very red object. We have low resolution spectroscopy of this object from both GPI as well as DLT sphere. And it's a very difficult atmosphere to characterize. The temperature estimates have ranged depending on the method that you use from 1100 to 1600, even 1900 Kelvin. And the surface gravities have ranged from a log G of 2.7 to 5. Also, the C to O ratio is not very well constrained for this object, so it's very difficult. Another reason why it's cool is this is a multiplanetary system. So VLTI gravity showed that there was a planet C, a 13 Jupiter mass planet, separated 2 AU from the host star. And then there's also a candidate that has yet not been detected. Both B and C are inside of a circumstellar debris disk, so they're very interesting objects to study. So here I'm plotting a GPI spectra of He2O6b along with 3 Phoenix ACES models. And so you can see these models are scaled to match in the peak of K band. And then we see this massive extinction between what the self-consistent models tell us we should be getting and what we're actually seeing. So now I want to show you the K-thick spectrum of this object. This is in K-band from 2.3 encompassing the CO bandhead to about 2.5 microns. Stellar glare is a real problem because of the close separation of this object. So we use a forward model that simultaneously models the stellar and planet light. And then we take a grid of self-consistent models and using a Bayesian inference framework, we can start to do some analysis about the properties of this atmosphere. So the result of this is we tend to be on the higher side of the temperature range, about 1600 Kelvin, with a log G of 4.55. So those are kind of the results that have been consistent with a self-consistent model grid. And we also derive a spin velocity of about 10 kilometers per second. That equates to a 14-hour day on this object. So we can also do a statistical measurement of the C to O ratio of this object. We keep the temperature and log G of this object fixed and then generate a grid of varying C to O ratios while keeping the metallicity fixed. And we find a solar C to O ratio, which is fairly expected for an object of this mass. So K-pick has been extremely successful in characterizing exoplanets and brown dwarfs. But we're able to resolve individual absorption features, measure abundances, et cetera. But I want to know what happens when you go to higher spectral resolution. Can you push it? What do you get? So one thing you get, if you're just purely resolving more lines, nothing else changes, you're going to get better detections of your objects. That's very true. The absorption features also get deeper as you move to higher spectral resolution, and you can start to disentangle some individual molecular features as well. On the other hand, you have to disperse the light more, so each photon becomes more precious. So what we really want is to be able to build a spectrograph that's purpose-built to go through for high resolution and conserve as many photons as possible, have the highest throughput possible. And so that's kind of why HiSpec is going to exist. So Mike gave a great instrument talk today, but I'll just go quickly through. HiSpec is a simultaneous YJHK spectrograph with an average resolution of actually about 110,000. We're a single mode fiber fed instrument. AO corrected light is coupled in to single mode fiber and then fed to the basement of Keck, where we have 2 stabilized spectrographs. And so this is going to enable us to have deeper atmospheric searches. So here I'm showing 2 isotopes of carbon monoxide, 12CO and 13CO. And here I'm showing absorption coefficient on the side. So if you're used to a absorption spectra, it's flipped from what you are used to looking at. But essentially, the difference between these two is due to the natural abundance of carbon-13. And so we really want to be able to measure this. You can do this with Osiris, with Keck Osiris, if you wanted to, and we've done it with KPIC as well. But it does help to move to distinguish these lines further with higher spectral resolution. Now, if you want to, I want to do trickier isotopologics though. So this is H2 versus H2 with 4 orders of magnitude lower natural abundance of 18O in this case. So you also don't have the nice like CO vibrational band head to go here. So it really helps to go to high resolution to suss out these complex absorption features. And then I want to say one thing about the improved radial velocity measurements that going to higher resolution gets you. But I'll leave Clarissa to say it. So please go talk to her if you have questions about that. I've also been working on the calibration system at UCSD for high spec. This is going to be very important to achieving all the science goals that we aim to get to with high spec. So this calibration system is going to employ 2 laser frequency combs, 2 astro etalons, a suite of gas cells, and a uranium-ion hollow cathode lamp to do absolute precise wavelength calibration and stable wavelength calibrations. And then we also have a custom data reduction pipeline that I'm really excited about and starting to come together. All right, I'll leave up my conclusion slide there and take questions.